in characteristics and solutions. And what we're doing now is we're continuing looking at how molecules and particles interact with each other. But instead of looking at pure things, as we did for most of chapter 13, we're now going to look at mixing things together, more like the lab that we did. And there's going to be some overlap in here with some of the things we did in the lab. So a solution is a homogeneous mixture. Remember from chapter 3, homogeneous mixtures of two or more. Sometimes it's more than two, but we're going to focus in on two in here, two or more substances. And solution can be any combination of gas, solid, or liquid dissolved in a liquid. Usually we're going to use liquid as we call it the solvent. The solvent is the major component. The major component of the solution. You can think of it as the active part. It's the part of the solution that does the dissolving. It acts on the other part, dissolves the other, does the dissolving of the other component. And it's usually going to be a liquid. There are things called solid solutions. Those are alloys. We saw those back in chapter 3 and chapter 8. Gas is harder to use, but liquids are very common. And some of the ones we saw in the lab, water, ethanol, hexane, those are all good solvents. A solute is the other part. It's the minor component. So it's usually the one that's present in less of an amount, and it's the one that gets dissolved by the solvent. So you can think of it as the one that's passive here. And often the solid can be a liquid. Often it can be a solid, or solute. Solute can be a liquid. It can also be a gas. But it can also be a solid. So I'm not sure what we're trying to say here. Sorry, a little typo. The solute can be a solid, liquid, or a gas. And we're going to talk about all three over the course of the next couple of days. Now, a couple of terms for us. Soluble is what you call Soluble is what you call something when it's capable of being dissolved. And we do have to specify being dissolved in a specific solvent. So as we saw in last week's lab, often something will be soluble in one solvent, but not soluble in another substance. Soluble, just as insoluble is the opposite. It's incapable of being dissolved. Dissolved in that solvent. Okay, so soluble and insoluble are the adjectives. Solubility is also a way of looking at it. Now, solubility can be both quantitative and qualitative. Today, we're going to look at it qualitatively. Solubility is just the ability to be dissolved. In a future lesson, we're going to look at as the amount of solute that can be dissolved. Again, these are both in a given solvent. And temperature is also going to play a role. Now, when we talk about liquids mixing with other liquids get a special name. And that special name is miscible. Miscibility is when two liquids are soluble in each other. That way they mix. And miscibility is different because often with liquids, you can mix them in almost any ratio. So you can start with pure water and start adding, say, ethanol to it, and then you can get all the way up to 100% ethanol or almost 100% ethanol. And those are called infinitely miscible. There are liquids that are immiscible, like oil and water. So two liquids that do not mix. And we saw some of that in the lab last week, and we'll talk a little bit more about that today as well. So what causes materials to be soluble in each other? So first, mixing increases the entropy. We talked about that as well. The entropy, the disorder or randomness in a sample, which is favored in nature. And we're going to keep coming back to this theme now for the rest of the year. We have a phrase. That phrase is like dissolves like. Oh, where did it go? Word keeps doing this to me. So like dissolves like. Now this is a mnemonic. This is a way of remembering it. This is not a reason. Please don't use this as a reason. If I ask you why something is soluble, don't tell me like dissolves like. If I ask you how you know something is soluble in each other, then you can use the like dissolves like. And that was that hypothesis we came up with, that materials with similar polarity are soluble or they will mix. And that mixing is a process. That process we call solvation. It's a process of mixing, the formation of a solution. And in that formation, we have an interaction, and the interaction always takes two parts. That interaction is between the solvent and the solute. And the interaction takes the form of intermolecular forces. And so let's look at how those intermolecular forces affect the solubility. So substances mix for a couple of reasons. One reason is that they have strong attractions to each other. They have adhesive forces, or they can also have weak attractions to themselves. And that gives us weak attractions to themselves. The cohesive forces take effect in terms of preventing, we'll see this later on, preventing mixing if we have strong cohesive forces. And starting off with polar solvents, let's take a look at what happens when you start to put different materials into a polar solvent. First material is an ionic compound. So we have water, a very polar solvent, and we're going to put some sodium chloride into the water. Now, what happens is the ions are attracted to the positive and negative ends of the dipole. Those should probably have a delta plus and delta minus of the dipole of water. And that gives us what's called an ion dipole. Now we can have something that has two different kinds of attraction because we have two different kinds of materials, an ion dipole force. And this is an adhesive force, and it's strong. There should be an N in there. Let me rewrite that. Strong. Because ions have full charges. And the process I have shown to the right here. So here's our sodium chloride crystal. And we have our chloride is the green and the sodium is the purple. And what's going to happen is the water molecules come up and they gang up on the sodium chloride. So we have the partial negative of the oxygen here coming up on that plus sign of the sodium, and they form this attractive sphere. This process here is the process of solvation. And they form this sphere in water, and this is how the substance actually looks. Now, there's actually 6 water molecules around there. I can only show 4 without blocking the sodium, but there should be another water molecule in front, another water molecule behind. Meanwhile, we have the negative chloride here, so the partial positives of the water attack that chloride. So there's our other salvation, and coming out and showing us how the chloride exists. Again, there should be 6 water molecules surrounding that. And those forces there over here to the right, these are our ion dipole forces. And again, they're strong because of that that large full charge. Now, sugar C6H12O6 is a polar compound. When it dissolves, it doesn't split up into ions. Instead, what happens is, because we've got sugar has a lot of OH bonds. And if you look down below here, this is sugar dissolving. And here I've got a picture of sugar. And you know what? Let's just blow that up for a moment and take a look at what's going on there. So in sugar, we have lots of OH bonds. It's hard to see them. Let's see if I can highlight them here. So let's see, what's a good color? Let's use green. So you see there's an OH bond. There's an OH bond. Those are all on the sugar. And those are now going to attract the water molecules. The water molecules are going to become hydrogen bonded to that sugar via the hydrogen there. So what's going on here is, instead of having an ion dipole force, we have dipole forces. Oh, I thought I had my pen. We have dipole forces, dip forces. They happen to be between 2 different molecules in this case, and because they both involve hydrogen, we have hydrogen bonding. And these are strong adhesive forces. Adhesive, again, being between 2 different molecules. All right, so this is how molecules that are not ionic can dissolve in water. Now, you can also, as we talked about in the lab, weakly dissolve nonpolar solutes like oxygen. So if we look down below, here's an oxygen molecule, and it's a nonpolar oxygen molecule. If you put that up next to this permanent dipole of the water, what's going to happen is the negative end of the water is going to push the electrons on the oxygen molecule away. And when you do that, we now have the attractive force between the positive and negative dipole. And we get this dipole-induced dipole. Let's write that up here. It's a dipole-induced dipole interaction. This is what the nature of dispersion forces is. They're very weak because they have very small delta plus and delta minus, very small positive and negative charges. But they're strong enough to provide enough oxygen in solution for aquatic life to breathe. And the aquatic life breathes the oxygen molecules. They get that oxygen molecule through their gills. They're not chemically breaking apart the water into oxygen. They're getting that dissolved oxygen out. Okay, turn the page. Now let's see what happens when we have nonpolar solutes trying to mix with polar solvents. And again, we talked about this, hexane in water. So when you have hexane in water, the hexane in the water do interact via dipole-induced dipole forces. However, in this case, because the induced dipole in hexane is very, very weak, it's too weak to prevent the hydrogen bonding. So we try to mix it together. So we try to mix, and as we try to mix, we get the hexane mixed in with the water and the water mixed in with the hexane. But what eventually happens is, because the water, that's not going to show up very well here, the water is more attracted to itself. Again, it's not that the water is repelled by the hexane, it's just that it's more attractive to itself. So H2O, let's write that in the line up here, has strong cohesive forces. stronger than the adhesive forces between the molecules, and stronger than entropy. So it overcomes the effect of entropy as well. And those strong cohesive forces are going to take that hexane molecule and push it out. And it's going to take that lone water molecule, and eventually that lone water molecule is going to sense the other water molecules and come back together. Now, why do two nonpolar materials mix? Again, we saw this before, but it's worth going over again. Remember, two nonpolar molecules have only dispersion forces. We can start labeling dispersion forces, London dispersion, LDF forces. And so, because we only have those London dispersion forces, they're only going to dissolve other nonpolar molecules. There's no strong interactions between the molecules. So the molecules, the cohesive forces, and this is what I was referring to up above, are not strong enough to prevent the other materials from getting in between. So instead, we get that increasing disorder. That entropy effect that causes mixing to occur. Again, we have energy. So the temperature gives us energy to cause the mixing to happen. And it will happen very slowly on its own, or it'll happen a lot faster if you do mix it together. So that gives us our lead into the next section. What can cause up, assuming that we can have a solution being formed, what can cause the rate of that solvation to speed up? So 3 factors can affect the rate of solvation. First, stirring or agitation. So stirring and agitation, this is like when you take a spoon and you stir it, or you take something and you shake it up. What you're doing is you're doing 2 things. First, you bring fresh solute. Fresh solvent to the solute. So if you're trying to stir up some iced tea, the top of the iced tea gets the sugar first, you mix it up, and as you mix it up, the bottom of the iced tea that was more pure water before, more pure tea, will start to have the ability to dissolve as well. The other thing it does is it brings in more energy, and more energy gives us a faster molecules. And if you do really sensitive experiments, you can actually measure the heating of a liquid by stirring it. It's very sensitive, though. We don't have that kind of equipment in our lab. Again, heating, going to a higher temperature, faster molecules, more kinetic energy. And so that solvation, they're going to bump into each other more. Think about the water being attacking the sodium chloride. Faster molecules is going to give us faster attack. And then finally, one thing we're going to think about is the surface area of the particles. So here we have a sugar lump. And it doesn't look like lump, does it? It looks like BIMP. Sugar lump. And in the sugar lump, the water molecules are trying to get inside, but they can only attack those 6 sides that are available to us. If we cut the pieces in half, so we cut it in half in each direction, what we're doing is we're going to get twice the surface area. So now that water can get inside those cracks. And since it gets inside the cracks, it has twice the opportunity for interacting with the solvent or the solute. Remember, you have to have solvent and solute interacting. If you cut each face by 1/4 into quarters, then you're going to get 4 times the surface area. Into 8ths, we get 8 times the surface area. And if we go to a powder is basically, say, millions times the surface area of the lump. So if you cut it into 1,000,000 pieces, you get 1,000,000 times the surface area, and it's going to dissolve a lot faster. So a smaller particle gives us more exposure of the solute to the solvent and increases that solvent solute interaction that we need. Interaction that we need to form the solution. Okay, so this is our look at how solutions form. Subsequently, we're going to look at some factors that affect the ability to form solutions, and then we're going to start to quantify. And in our lab next week, we're going to have some quantified solutions and trying to look at how to look at solutions and how to know how much solute you have in a given solution. All right, so that's just little something to get ready for next week. Meanwhile, you have the homework, and have a great day.